Today in this video, we're going to be covering a couple of different sections, and I suggest that maybe you take a little bit of break in between the first one and the second one. I'll prompt you. I'll tell you when that's going to be, but we're going to cover a lot of stuff today about statistics. I found this statement here, and I will refer back to this again throughout the class as we go. This statement is statistics. It's a science. Some would refer to it as a math, but a science partly learn from trial and error. There's things we're going to cover today that's pointing out errors. There are errors in collecting data. There's errors in what you do with the data, generating the statistics. There's error in interpreting the statistics. There's error in presenting the statistics. And there's error in further calculation with the statistics. So there's a lot of errors involved, and over the time, a lot has been learned. Statistics actually is a very young science, math, if you would. It's only been around for a couple of hundred years, the study of statistics and how we analyze things using statistical tools. And so in that time, there has been a lot of stuff that's had to just been learned through error. That they would try something and, well, you know what, that just didn't work real great, and maybe there's a better way to do it. I want to throw these out here. Some quotes people have stated about statistics, at least the top part are quotes. The last thing is not a quote. But the first quote is this: there are three kinds of lies. There's lies, there's damned lies, and then there's statistics. This is from Benjamin Disraeli. He's the former British Prime Minister. Disraeli. Sorry, I mispronounced that. Here's another one. Figures don't lie, liars figure. That's by Mark Twain. I'm sure you've heard of him. Then there's this one. There's two kinds of statistics: the kind you look up and the kind you make up. And that's by Rex Stout. And then there's this one: 58.6% of all statistics are made up on the spot. That'd go along with what Rex said right there. And that is unknown, and it's sort of a joke in statistics that, yes, a lot of stuff truly is made up on the spot, unfortunately. And that's part of what I'm hoping that you'll develop a critical eye to see that people make a lot of errors, and then beyond that, there's people that just make stuff up. So you always need to be careful when you're taking a look at statistics. This is not a quote, but a 2009 investigation survey by Dr. Daniel Fanelli from the University of Edinburgh found that 33.7% of scientists surveyed, and scientists are trained to use statistics, keep that in mind, admitted to a questionable research practices, including modifying their results to improve outcomes, subjective data interpretation. We're going to talk about biases. This is referring to bias. Well, this is bias in interpretation. There's also bias in collection. Withholding analytical details and dropping observations because of a gut feeling. Later on we talk about outliers. There are sometimes outliers when you collect data, but it's not a matter of dropping them due to a gut feeling. There's actually a process to decide if it's far enough away from the rest of the data. At what point do we drop it? So there should never be a gut feeling like, well, that was probably a mistake. I think I'll just not include that one. So I'm sure you've heard of fake news, which, you know, and in the last few years, people have actually started to accept that, yeah, you get onto Facebook, some of the social media stuff, there is fake news out there. If you research that at all, you'll run into stuff like this, how to spot fake news. And of course, they've got these methods, consider the source, read beyond, so on and so forth. I find it kind of ironic that when you go through the how to spot fake news stuff, it's very similar to what we're going to cover today on how to watch out for misleading statistics. So, I don't know, just if you've thought about this at all, well, you've sort of actually already thought about this, and that's where we're going to go with this. Here's just a little chart that has to do with occurrences of fake news. You know, we didn't really hear about fake news till President Trump started talking about it. That's why 2016, that's why they started watching for it then. So within just a few months, the climb of fake news. I want to make a comment here about this, though, even though this particular thing is about fake news, not misleading statistics. I would look at this and say, well, this was a misleading presentation of statistics, because I would argue that that's a bad graph. And we're going to be talking about bad graphs, not today per se, but we're going to take one whole day and just look at bad graphs. Here's another one. In 2007, the toothpaste company Colgate ran an ad. Oh, sorry, I have a spelling error there. It's supposed to be two D's. Ran an ad stating that 80% of dentists recommended their product. Based on the promotion, many shoppers assumed Colgate was the best choice for their dental health. Okay, so there was an ad ran that presented a statistic. 80%, that's a statistic. It's not a data point, it's statistic. They've done something with it. But you dig into it a little bit more, and it wasn't necessarily true. In reality, this has become a famous example of a misleading statistic. Is it a statistic? Absolutely. And statistics make people believe things because they figure, hey, if this person knows numbers, they must know something, so I should believe what they're saying here. People are influenced by numbers. The ad suggested that the dentist preferred Colgate over other toothpaste brands, but the survey asked them to list several brands of toothpaste that they would recommend. So they weren't studying specifically Colgate. They listed off a whole bunch of toothpaste, Crest and Colgate and others, and they said, hey, of these, check the box that you would advise your patients use. Well, it was just one of many that was checked. But of course, it was checked on 80% of the ones that dentists took a look at. And so this is a misleading statistic. Was it a statistic? Yes, it was. 80% of dentists checked the box that had Colgate. But they checked all the other boxes too, probably. And so it definitely was misleading. All right, by the way, I guess now that I rethink it, that's not a spelling error. Too much math. The data only showed that Colgate was one of a number of different brands that the dentist did like, as actually what should have been concluded. Okay, so causes. We're going to talk about the causes of misleading statistics. Misleading statistics are data points or sets that lead readers to believe something that isn't true. This is important. Lead readers are leading them along. There's 3 stages in the data analysis process where this possibly can occur. One is just in collecting the data. There's bad sampling methods, and we'll be talking about sampling methods still today. Later on. So in how you go about collecting it, biases can be introduced here, and I'll talk more about biases. A bias can create a bad collection process. Just bad planning can create a bad collection process. The processing, okay, so now you've got the numbers, how you actually calculate them. When you analyze them, there can be mistakes made. And please understand, these can be on purpose, but these can also be just purely on accident or out of naive, especially this part, the processing. I think this is how you do it, but it turns out maybe that's not the way that you should have actually calculated that. So in the analyzing, there can be mistakes made there. But then also in the presentation, when you share the results of your analysis, when you share them and how you share them and how you present them to people, that also can be a source of misleading statistics. So I'm just going to throw this at you real quick. The Colgate one, where did they make the mistake? Well, maybe it wasn't a mistake. Let me restate that. Where did the misleading statistics show up? In how they collected, and how they processed, or in how they presented? I'm going to let you think about that. Some sources of misleading statistics. So there's a lot of these. I'm just warning you, I've got pages of this stuff. Your sample size is way too small. I've used this example before. Let's say we want to find the average height of all 17-year-old boys in the high school. I go out into the hallway, I find one 17-year-old boy, I measure how tall he is, and I declare there's the average height. Anybody would recognize, I think, that it would be a source for at least a strong possibility of a misleading statistic. I suppose there's the probability that I, by accident, actually picked the one kid who represented the average height. That is a possibility. But more likely than not, it would not be the average height. Okay, because my sample size was too small. I'm not going to go through and measure every boy. I'm going to collect a sample. All right. Leading survey questions, or leading question. So I'm going to throw this one out there. Would you agree that I'm a better teacher than Modest? There's a leading survey question. Check your surveys for manipulative wording that might lead respondents to give a particular answer. A few examples of influential phrasing include phrases that ask for confirmation. That's what I'm doing to you right here. I'm asking you to confirm that I'm biased and think that I'm a better teacher than Modest. And by the way, you can go ahead and tell him that I'm using this as an example. I know he likes to banter with me back and forth in lessons. Okay, so that's me doing that one right there. That's a leading question. Okay, so that's one way. There's actually lots of these. I didn't list them off because this list could go on forever. Loaded with emotion. Words like disaster or amazing. Absolute terms like all or none. I find this funny. I recall way back when, to my premarital counseling days, we were warned about the same stuff when it came to arguing with your spouse. You know, avoid these all absolute terms like all or none, or the emotionally charged words. You're supposed to avoid those. Well, you're supposed to avoid them when you're putting together a survey as well. And like I said, you could Google this, and there's just hundreds of examples. I'm stopping because I just am. Confirmation bias, okay? And maybe you go back to my statement up here. Yeah, I think that's a leading one, but you probably could argue that's a confirmation. I'm trying to confirm something based off of my own bias. And by the way, I don't actually feel this is true. This is the set result you want to see, so you're looking for it. You're looking at only the data that affirms your belief. I'm collecting statistics on students that agree that I'm a better teacher than Modest. And if you don't agree with me, well, maybe I'll say that's an outlier and I just won't count that. That would be a confirmation bias. Okay, so that's definitely a source. The remedy for this is this. This is not a source. This is the remedy for this particular one. Get a third party to review. When you're all done, get somebody else's eyes to look at this and go, hey, what do you think here? Do you think I had any confirmation bias? There's a lot of research done where there might be confirmation bias, but it's not necessarily malicious. What I mean is they may not have intended it to be that way. So keep that in mind. Third parties, bring somebody else in and say, hey, do you think I'm doing this right? Confusing graphs, charts, and labels. We're gonna spend a day, or at least a piece of a day, talking about bad graphs, bad charts, okay? Because that's actually a big topic, and there's a lot of things to talk about there. Mistaking correlation with causation. So here would be an example of that. Sales went up around the same time that you released your marketing campaign around a new product feature. Okay, did the sales go up because of the marketing campaign? Well, maybe they did. There's correlation there that sales went up about the same time as the marketing campaign for this new product. But that doesn't mean that it caused it to go up. It could have been maybe something else. And there's actually statistical tests, and we probably won't get this far in elementary statistics. This is an introduction to statistics course. There is a calculation test that can be done in a more advanced course to actually check and see, hey, was this caused by correlation or was this caused by causation? Did the marketing campaign cause sales to go up, or did it just happen that they went together? There's a lot of business applications to statistics, and you'll hear me talk about that stuff. I told you I got a lot of these things. Incorrect usage of percentages. People just don't understand percentages as a rule of thumb. They really don't. And I'm going to have you guys in my class critiquing an article that later on that actually shows you the misusage of percentages, how the author, and it was a published article, was misusing percentages because, quite frankly, he just didn't understand. Or I would like to think that he didn't understand. The other argument would be, well, he was maliciously trying to manipulate, which I suppose is a possibility. But incorrect usages of percentages. Loaded questions, which are kind of like leading questions. Should the president have the right to declare war? There's a question. Should the president have the right to declare war on ISIS? There's a different question. Should the president have the right to declare war on Canada? Notice in a loaded question, and this is sort of then playing off not only just your emotions, but your logic. Because I throw in a word like this, that inspires an emotional response. I throw in a word like this. Probably, unless for some reason you really don't like Canada, probably a quite different emotional response. So it's a loaded question. When you give a question like this, you need to continue on and be very specific, because as you can see, being specific can make a big difference in how people would respond if, say, you were running a survey on whether a president should be able to declare war all on his own. Giving this survey the day after a president declares war, which obviously would be an emotionally charged day, is also then maybe bad timing. But the loaded question part has to do with not being specific to it. Orders of the questions. People don't necessarily think about this. This is actually a really hard one to catch, and I'm going to stress the unintentionally. People can do this unintentionally very easily. Again, not necessarily malicious. But survey questions can be unintentionally or intentionally loaded, so they become loaded questions, based off of the order of the question. For example, would you say that the traffic contributes more or less to air pollution than industry? When it was asked this way, 45% blamed traffic, 27% blamed industry. Same survey, except you flip-flop which one came first. So same question, basically, it's just the order. Would you say that industry contributes more or less to the air pollution than traffic? When it was stated that way, 24% blamed traffic, but 57% blamed industry. It's just a slight little thing. Most time you wouldn't think that, hey, just putting it in a different order could actually change the results of a survey. But it does. And so what you have to do here is somehow separate them, or offer the question. You could fix it by doing something like this: offer them in different orders, equal numbers of times, and then average that. So that's maybe a solution to something like this. But it's a little bit of a loaded question because of the emotions attributed to the way that it's stated. All right, I got more of these things. Non-response. Surveys, people that refuse to take a survey, okay? This occurs when they refuse, or let's say that you put out a survey on a social media platform and people get to choose whether or not they want to actually participate in the survey. Well, there's a lot of people that probably choose not to. And by not including them, you are not getting a good representation of the actual population, because you're only getting results from people that probably have an emotional attachment to whatever the issue is. Those that refuse to take polls are more likely to differ. Whatever the topic of the poll is, if they don't like the topic, they usually refuse to take it when given a choice. A little psychology here. Well, if they differ, then what you're doing is you're weighting your results more towards those that agree with whatever the poll question has to do with. So there's a huge error that can come with non-responses. So social media surveys, mail-in surveys, or I've received mail-in surveys. I actually have one sitting on my island at home right now. I'm supposed to fill out. I'm not going to do it. I'm going to be one of the non-response people because I really just don't want to. it can really skew the results. Surveys in general, where people are given the choice to do it, are considered a horrible technique when it comes to statistics. And this is related to another one that I'll get to in a minute here. Missing data. Results can sometimes be dramatically affected by missing data. In the U.S. Census, people that are homeless, well, they don't get counted. Homeless people don't get counted, and so because they don't have an address. So there's missing data. Well, this can totally change the results of the presentation of the population that actually lives in a certain area. Specifically, the southern states have more homeless people than the northern states. But it doesn't show up in the census because they don't have addresses. So you're not really getting a complete picture when there's missing data. Self-interest study. We need to be very careful, very wary of study results when they sponsor. That's the person paying for it. It costs money to run surveys. Paying for the study stands to be set up for a monetary gain. There's a magazine, Car and Driver, I think is what it was. There's a couple of these car magazines, and I don't remember which one it was, but there was a time when one of the manufacturers bought the magazine, and then every time they did a comparison of different manufacturers, their car happened to be the winning car. Until finally they were like, okay, the people stopped buying the magazine because they realized it was kind of a rigged deal. And so they sold off the magazine again. So I don't believe Car and Driver is owned anymore by a manufacturer, but I think there was a period of time when it was. And that would be they were having self-interest studies, that particular manufacturer, of course. They just always looked better than the other ones. Precise numbers. If you truly understand statistics, you truly understand there's always a level of error in data collection. And so really, really exact numbers, they mislead people because they're like, wow, here again, numbers just mystify people. They think that, well, they must really know what they're doing because they got so accurate on the results. You know, something like this, you know, you should round that to like 1 million people. Let's just be honest here. Whatever this study, I literally made this up. But if it was this close, I'd say, well, I don't know, 1 million people. Because they're estimates. When we gather statistics, especially from surveys, they're always just an estimate. There is error. And so you can't present real accurate data because we can't measure that accurately. This goes into the error in measurement as well. And then we've got deliberate distortions. There are people out there that will deliberately do stuff. They inflate numbers in order to gain an advantage, especially if there's money involved. Even research. You think about scientists with research. If they can maybe publish a paper, get notoriety, get hired by a more prestigious university because of it, they are tempted. I'm not saying that they all do it. I'm saying there is a temptation to make it go their way. Back to that one that I showed you, that statistic, that almost 1/3 of scientists admit to having tweaked the numbers in one way or another. Voluntary response samples. Let's come back to this one. I threw this out. This is one in which the respondents themselves decide whether they want to be included. So I don't want to take that survey, or I do want to take that survey. They get to decide. The freshman 15 example that I gave you on people that were weighed, and then 4, 5, 6 months later, they had to voluntarily come back to see if they'd gained weight. Well, of course, the ones that gained probably didn't want to admit it, or they didn't want to show it. They didn't want to be part of it. And so it's a great example of when a voluntary system, it really just doesn't work. Anytime it's a voluntary system, internet survey, hey, if you'd like to, please take this survey and send it back. Well, you're only going to get the ones that typically agree with it. The ones that disagree, again, typically don't do it. Following example, the following are common examples of voluntary responses samples which they are by their very nature, are seriously flawed. And because of this, we should not make conclusions when dealing with these. And this is a quote by the author of your stats textbook, Triola again. He has strong opinions about this, which anybody that's studied statistics does. Polls. Conducted through the internet. I've already mentioned that. That's a really bad way to do it. Social media, throw that right in there. Social media, mail-in polls. Believe it or not, that still happens. Like I said, I've got one sitting on my island right now. That a mail-in poll. Those are a bad way to do it. Telephone phone calls. You don't have to get these as much, but it used to be, especially during political election years, a ton of telephone phone calls. You get a lot of people, they just hang up. They don't want to do them. Well, there you go. There you now you have missing data. Newspapers, radio, television announcements that you have you voluntarily call in to some number to register your opinion, which again, a lot of this is now done. It could be text into this number or answer to, there was ways where you can just send in a particular number in a text and it'll register as a yes or a no. Any of that stuff. Those are all what are considered voluntary responses, and this is not considered to be a good sampling method. These are considered to be a bad sampling method every single time you see them. So as I have you guys try to put together some little bit of research, I would like you to try to avoid voluntary research. Misuse of graphs, and again, I'm going to do a whole day on this. Just a real quick example here of one misusage of graphs. If you take a look at this here, this one is wrong for a lot of reasons. One is the color. Another is, notice how much wider this is. Why is this wider than the rest of them? Is there a reason for that? This is, by the way, the average weekly Australian spending. And I'm guessing for some crazy reason, these people were really focusing in on transportation as a thing. I don't know what this was about, but transportation was definitely their thing. Oh, another one is, why is it in the middle? Why isn't it like the tall one, then the next one down, and the next one down, and the next one? It's really strange. It's right there. This is a really bad misuse of graphs. The last one here is, this is what's called a non-zero chart. Down here, does this represent 0? I actually have no idea because it doesn't show me. So then is it a good representation of the heights? Does the height actually mean something? It's hard to tell. So it's a bad graph. All right, if you want to take a little break, take a break before we get into the next section, or just pause it and come back. Okay, experimental design. If you're going to design an experiment, and please understand this is a statistical experiment, not necessarily what you think of as a science experiment, and I will talk more about that in a little bit. We're designing some statistical study. Here's some steps, and you should put these in your notes. Identify the focus of the population. Identify the focus of the population. Decide how you will collect the data. How will it hit the desired population, and how will the sample be random? This needs to be a detailed plan. Okay, now that I've got a couple things here, I'm going to go back and actually talk about this a little bit more. Let's say that you want to find out what percentage of people in America prefer pizza over hamburgers. Here would be an example of a bad way to design your experiment. I'm going to go through, pick a town, Pequot Lakes, Minnesota, Brainerd, Minnesota. Notice I'm staying within Minnesota. I'm going to pick a town. I'm going to randomly select people to ask them if they prefer hamburgers or pizza. Well, wait a minute. The focus of your population was the nation. If I said U.S., then the entire United States should be part of what could possibly be surveyed. So now, if I want to make it specifically about Pequot Lakes, Minnesota, oh, well, that's different then. Then I can conduct a study right here. But if it's over the whole United States, then I can't just limit my study to just one particular town. I'm not getting a good look at it. So this is why it's really important to identify, what are you focusing on? Are you focusing on the entire U.S. population, the world U.S. population? Let's say that in the manufacturer sector, you are looking at how You're manufacturing lots of car parts. Let's put that out. And you want to know, well, how many times do we have a bad part? Well, which parts are you talking about are bad? Are you talking about a bad alternator? Are you talking about a bad water pump? What's the focus of your population? So this means to get really, really specific and know what you actually want to research. Then you'll decide how to collect it. Because if it's a nationwide thing, well, then how you collect it's going to be way different than a local thing. If it's all the parts in the factory, or is it one of the parts in the factory, the focus will help you decide how you're going to collect your data, or at least which data you're going to collect. Then you got to do the how am I going to do this? How am I going to make it random? And we're going to talk more about why does it need to be random later on. This has got to be a detailed plan. Then you just go out and you collect your data. Then you're going to describe your data using descriptive statistics. Descriptive statistics we'll be talking more about later. This can involve graphs. It can involve presentations of the numbers. There's a time when you use numbers. There's a time when you switch over and you should be using graphs. And then depending on what your goal is here, you might need to interpret the data so that people can make decisions. Again, this is actually kind of the first part of statistics. This has to do with the second part of statistics. But this is how you design an experiment if it's a statistical study. Last thing, you always want to look back and identify possible errors. Did I introduce a bias somehow, even intentionally or by accident? A lot of things will have errors. And so you've got to take a look at that. I'm going to make one more comment back here about being random. The short version of whether things are random or not is whether you did the picking. You can say, well, I went into a crowd and I picked every fifth person. Okay, but you picked them, so it's not random. Randomness has to allow something that isn't possibly introducing a bias. And so we'll talk more about that later on, but basically, if you're involved in the picking, it's not random. Okay, identify the focus of the population. Focuses are what you're studying. The population is the group that you're studying it from. Identify the focus in the population. Study the effect of exercise. Okay, so a study of the effect of exercise, or a study of the effect of exercise on relieving depression. You realize how detailed, adding that little detail there all of a sudden can really change things, because this is a very unfocused statement. This is a focused statement. So now I'm really getting detailed and identifying what do I actually want to study. A study of the success rate of graduates. Okay, that's a horrible statement, because what do you mean by success rate? You might be talking about money. You might be talking about buying a car. You might be talking about getting a date with a girl. I don't know. Success at what? So that's a really bad statement. A study on the success rates of graduates at a large university in finding a job within 1 year of graduation. Specifics and details. Specifics and details. When I ask you to write out a focus statement, I need specifics and details. Nobody should be able to come along and punch holes in it by going, I really don't know what they're talking about. When you do this, it also tells you your population. Notice in this one, my population of A, so they probably have a specific university in mind. And I would say even here, I wrote it out, but maybe we mentioned, say, University of Minnesota, Duluth. Okay, so then that dictates where I'm going to go collect my data from. Now, if I wrote this a large university, well, I would need to define what's large, and then I would need to possibly visit every large university in order to answer this study. But at least it's more specific than my first one. Here's what you should be thinking when you put together a focus question. What are you really trying to answer? We're going to discuss this as a class the next time we meet. And this is a study that I found, and I want you to just notice how specific this is. Simon Fraser University Health Sciences researcher Julia Smith is a co-leading new research, or she is co-leading new research on how rapidly developing infectious disease outbreaks. Look at all these specifics. Rapidly developing. So not just developing, rapidly developing infectious diseases. Okay, so we have different kinds of diseases. She's very specific. The infectious diseases that qualifies as an outbreak. And I'm not sure how they qualify what makes an outbreak, but I would assume in the medical research community, they would understand what that means. Like COVID-19, I know that they're calling it an outbreak. Impacts genders differently. I read some about this. I didn't put it all in here, but it had to do with, the distribution of the vaccine. How it actually, so they're looking at that. So looking from a social, this actually is still a big question. The social ramifications, the biological ramifications. Do men actually get, I'll use a vague term here, sicker than women? Or do women get sicker than men? Okay. And this is because her focus really entails the entire world. Her team is throughout the entire world. Her team, now, I don't have it all here, but her team included scientists from just about every continent. I noticed there wasn't one from South America, but she had Asia, she had Africa, she had Europe, and she had North America. And so they were really taking a look at a large scale. They were looking at the entire population. Otherwise, she would have had to put in here, say, in Northeast United States or something. But she left it open, which entails the entire world, which of course then means she has to study the entire world. Questions: what is the focus? What is the target population? I want you to be able to answer that for me when we get back together. If you didn't notice, I kind of already gave it to you, but we're going to talk about it when we get together. Here's another one we're going to talk about when we get together. From October 2017 till May 2018, a study of men and women in Edinburgh and, I'm not sure how to pronounce this, Lothians will be assessed to find out whether, I think that's the wrong weather there. That one actually wasn't me. That was them. Consuming antioxidant-rich cocoa powder will play a role in maintaining and preserving brain power and general health. Again, this is a very specific statement on what they're researching. This will be conducted by scientists from Queen Margaret University and accomplished with a series of cognitive tests. So now they're actually describing how they're going to collect their data. Questionnaires and body comparison tests. I think this is probably why it's over a period of time. I'm assuming they'll do pre and post checks on cognitive and body, with questionnaires probably somewhere in between. When we get together, I would like you to discuss what's the focus and what's the target population. All right, some vocabulary. A census is a count of an entire population. A sampling, a count of only part of the population. Sampling error, the difference between sample results and the actual numbers in the population. If you're just doing a sample, there's always going to be an error, and that's what we're talking about. It's just a matter of how much is the error. And usually the key to keeping this low is having large sample sizes. We actually do calculate later in class, like in a couple months. We can do calculations on, well, how big of a sample size do I have to have my error be down to? And then you just pick a number. How low do you want to make this go? It's always assumed that there's sampling error. Not that the sample was erroneous. It's not that you did it wrong. It's just assumed that there's error. There just always is error. Just that if a similar sample was taken, there would be a difference in the chance of sample fluctuations. Okay, let's say that you're doing, again, let's use these sample height. Okay, so now I randomly selected 30 17-year-old boys in the school and sampled their height, got an average height. I would assume that it is probably decent, but it probably has some error. And I could show you that there's error by doing the same exact thing again, by randomly selecting 30 different male 17-year-old students. And most likely, I will get a slightly different average height. thus showing you there's a sampling error. Again, not that I did anything wrong. It wasn't that my study would be erroneous. It's just that anytime you're doing a sample and not the entire census, there's going to be error. Non-sampling error. Error is not because of chance samples, okay, not because the 30 boys were a different group of boys, not from that, but because the sample data was incorrectly collected. Okay, so this is one where basically it is their fault or it's your fault because you're biased, you're sloppy, or you've got bringing in the biases and sloppy. I'm throwing that in there because you're sloppy or you're biased. Defective measuring, that would be the sloppy, or just plain copying down your data incorrectly. You weren't really paying attention and you switched some numbers. There's a ton of ways that the human part of collecting sample data can introduce an error. This is the non-human part. This is just simply probability. This is the human part. Biased samples, not representative of the population. Anytime it's biased, it will not be a good representation of the entire population. So you got to decide how you're going to collect your data. There are 4 ways. I'm going to focus in on 2 of them because 2 of them are not considered great. The one is called an observational study. You simply observe the sample. The second is an experiment, or researcher applies a treatment. Notice I put this in red. I really want you to notice here we're talking about a statistical experiment. In a statistical experiment, unlike one in a science class, a science lab, science you have an independent variable and a dependent variable. In a statistical experiment, you have a treatment group, and then you have an experimental group. You have a treatment group that you perform your experiment on, and then you have a control group known as the placebo group. Okay, so one group is, think medical research here. A group of people are going to get the medication or whatever the treatment is. And then another group is not going to get the medication or whatever the treatment is. They're called the placebo group or the control group. And then you're doing a comparison between how the 2 reacted. That's a statistical experiment, not a science experiment. Please make the distinction. Notice these 2 are bold. These are the 2 main ones that we're going to be looking at. There are simulations. We haven't really got into the ethics of statistics yet, but let's say that I want to study the percentage of people that can survive an airplane crash. Well, I suppose I could get a bunch of volunteers to park their butts into airplanes and we could crash them and we could see what percentage actually survive on average. But that would not be ethical. So in those situations, if it's unethical or maybe just physically impossible, then we will run mathematical or computer simulations is what we'll have to do. And then there's surveys. Surveys are asking the population or sample to respond using interviews, mail, telephone, social media. I should have that in here. A weak version of collecting statistics. Now, I know that as a class, this one's an easier one to do. And so we probably will do some surveys because you can still get information from them. But you really have to be careful to have it randomized, and you really got to be careful not to introduce biases. And we'll talk about that. How do you avoid introducing a bias? Side note, sometime I already covered this with you guys, the difference between a science class 1 and a statistical. Statistical experiments have a treatment and a control group. Please be aware of that. That just might show up on a test. All right. Let's talk about deciding how you would collect the data. So you got observational studies, experimental studies, survey studies, and simulation studies. Which one do you think would work the best? A study of the effect of changing flight patterns on the number of airplane accidents. Okay, I basically gave this one away. Yeah, you're going to want to run a survey. Not a survey. You're going to want to run a simulation on that one. This is just not ethical. A study of the effect of eating oatmeal on lowering blood pressure. Well, observing is you sitting there with a clipboard and making marks on what you see, which I suppose you could do that. But in this case, this seems to be a medical. Pretty much all medical studies are, I'm just going to tell you, they're going to fall under experiment. So you'd have your treatment group, you'd have your placebo group, and you'd, compare what oatmeal actually does. I think that one's actually been done. I think that's a study that's been done. A study of how fourth graders, students solve puzzles. Okay, so it'd be tough to do a treatment and a placebo group here, because what's the placebo doing if they don't have a puzzle to do? So this one probably is sitting around with a checkboard doing an observation. By the time you're done, because you just have such a huge headache, you probably will wish you had done a simulation, but observational would probably be the best study to do with that. Study of U.S. residents, approval rating of the U.S. president. Okay, well, these are done all the time, constantly, and those are always surveys. A study of the effects of exercise on relieving depression. Okay, again, you could probably do that with a survey, but if you really wanted a quality study done, this would be a great experiment. You'd have a group that didn't exercise and a group that did exercise, and you would compare the relieving depression. You have a really tough variable here, though, based off of, there's a lot of things that can possibly be relieving depression, though, other than just exercise. Maybe the day they take the they go through the experiment, maybe it's a sunny day that day, or maybe it's a cloudy day that day. You'd have a lot of what are called confounding variables, but I would still say that that would be an experiment, would be your better choice there. But maybe observational or surveys would be decent as well. Okay, I'm going to be specific here about an observational study. This is just observationals. You observe and measure, but do not modify. You're not changing anything. In an experiment, you are. You've got your treatment and you've got your placebo. And observations, once again, you're basically, it's kind of like you with a clipboard kind of deal. You can do it in the past. You can do it in the present. Or you can do it in the future. And they have different descriptions here. In the past, it's referred to as retrospective or case control. So the data is already there. You just go find it. You go back in time and collect data over some past period. Okay, so you have information on, let's say, the number of students that graduated from a particular high school over a certain number of years, and what percentage of them went on to a four-year university, what percentage went on to the military, so on and so forth. That would be a retrospective. The data's there. You just got to go look for it. You got to go find the data, look it up, and then you can put together your observation. You're still observing the data. You're just doing it with data that's already been accumulated. At a point in time, okay, so that's what's referred to as a cross-sectional study. You're picking a point in time. Right now, I'm going to go take my little clipboard and I'm going to go study something right now. That's called a cross-sectional study. So retrospective or case control are looking to the past. Cross-sectional is at a point in time. Data are measured just at a single point in time. And then in the forward-looking, you've got what's called prospective. And this actually is probably used more often. Our textbook uses prospective, but this is the word I hear a lot more, is longitudinal. I don't hear cohort very often, but longitudinal, that one I do hear. It's the idea, what you actually are doing here is you are typically starting a study and then you're letting time go by until you gather your data. There's a pretty famous study out there about giving kindergartners marshmallows, and it's called the delayed gratification study, where they promise that if they wait 3, 4, 5, I don't know what the time was, minutes, they would get a second marshmallow. But if they ate it right away, they didn't get a second marshmallow. And then 12, 15, 20 years later, they went back to see the ones that could delay the gratification. Monetarily, were they more or less successful than the ones that couldn't? So there was a They started the experiment, but then had to wait a long time to actually finish the experiment. That's a longitudinal. I think of the long. It takes a long time to do these. It's really what's going on. 3 keys to designing a successful experiment. Control. You got your control group, you got your experiment. But you got to have control. Must be able to control all factors, kind of like that depression one. Well, okay, can you control the weather? You might not have a real successful experiment if you can't control the clouds or the sun. Randomization. Must assign groups randomly. Randomly, again, is the idea of you're not the one picking who or what gets picked. Replication. If you did the experiment again, or if someone else did the experiment again, and in the real science world, it's a someone else. Someone else will come along and they will follow your methodology exactly and see if they get the same results. So if randomizing is so important, we got to talk about how to randomize. In a random sample, members from the population are selected in such a way that each individual member in the population has an equal chance, every member has an equal chance of being selected. So there again, if you're studying who likes hamburgers and who likes pizza better in the United States, you cannot just restrict where you're getting your numbers from to a single town, because you're applying it to the entire United States. So anybody in the United States would have an equal chance of being selected. So that's what random means. Every member of the focused group in the every member of the population that you're focusing on has an equal chance of being selected for the sample. A simple random sample of n subjects is selected in such a way that every possible sample of the same size has an equal chance. So now you're talking about groups. So so groups have an equal chance of being chosen. You're taking an entire group at a time, where up here you're taking a person at a time. So take this for example. Of the population of patients with lung cancer in 25 different states, a study selected 5 states. From these 5 states, they will group the patients into groups of 100s. From these randomly selected chosen groups of 100 patients will be chosen to participate in a clinical trial in a new treatment. Notice that out of the 25 states, every state could have possibly been chosen, and then within those states there's groups of 100, and each 100 could have possibly been chosen. We are selecting in groups here though, so this is a simple random experiment. It's confusing because simple makes it sound like it's somehow easier to do. What it is, it's easier to get big numbers, is what a simple random is. So the question is, do all the patients in the 25 states have an equal chance of being selected? Yes, but it's in groups, so this is a simple random. Do all sample sizes have the same chances of being selected? All groups of 100, do they have just as equal chances of being selected? Yes, they do. So that's simple random. Other sampling methods, they can/should still be random, okay, which again means everybody has equal chance of being selected, and you're not the one doing the selecting. I throw that in there, but the actual definition is everybody has equal chance, or every group has equal chance. Okay, so the first one is what's called a stratified. Stratified sample, and again, it's still going to be random, but a stratified sample, a population is divided into subsets or strata that share a characteristic like age or gender, something like that. And then they're chosen randomly from each subset. Okay, so we've got, maybe we got young, middle-aged, old, and then randomly from each group, they can randomly be chosen. Cluster sample. This one is probably most misunderstood. The key to this is somehow naturally divided itself. Okay, naturally divided. Now, when it comes to tests, I'm going to throw some of these at you, and you're going to have to pick. And I will just tell you, the cluster is the one that people get the wrong most often, so make sure you're practicing how to do these. You don't make the groups. Okay, something else whether it's actually in nature or something else has made the groups. But you choose one or more of the groups randomly. It's still a randomness in how the groups are chosen, not someone from each group. So you're choosing a group. Here's my naturally one. Let's say we have these rivers running through this town, and the rivers, well, I suppose these are roads. These roads running through the town, and it kind of breaks up the town into just different chunks, or this village maybe. The roads themselves sort of naturally break it up into groups. Another example, this might be if you're studying second grade behavior, and you go to a school that has 5 second grade classrooms. Well, the classrooms themselves are sort of choosing for you which group you're going to do. You just have to randomize which classroom you're going to pick, but the groups themselves have already been divvied up by the which classroom are they in. So that would be a cluster sample. Then you've got a systematic. You've got a systematic sample. Each member of the population is assigned to a number, and this is not you picking the number. You have to somehow have something else pick the number, roll a die or something like that. Choose every, say, nth member, so every third member or something like that. But the choice of the nth number should be random. Again, you're not the one picking where it starts. Okay, so you line people up and you number them off, and then we're going to go, okay, so we're going to start with the second person, and then we're going to go every third person. Now, randomness is you didn't pick the second person. You somehow had a machine or something tell you what number person you're going to start with. But what you did is you decided how often you're going to take the next one. So you can pick that every third person. You could have done every third, every fourth, every fifth person, but you did not pick which one started off with. Convenience sample. Not recommended. Star that. It's not recommended. These are really, really bad sampling techniques. Consists of only available members. Like, hey, let's go ask that kid. Okay, there was nothing random about that. Okay, going back up this, you got to be random. Convenience samples are not random, and it is so that's what I'm saying. It's not simple. It's not a group, and it's not just random because it's even if it's individuals. So there's no randomness to these. And then you got probability samples. Involves the selecting of members from a population in such a way that each member of the population has a known but not necessarily the same chance of being selected. A good example of this is like a race situation in a city. You're going to have such and such population that's black, such and such population is white, such and such is Hispanic, or such and such is Asian, whatever. And so then when you pull out your sample, and it still has to be random, every person in the black community has just as equal chance as any other person of being selected, is what that would mean. But in your entire sample, 25% of the people in your sample will be, in this case, black, 60% white, and 15% Hispanic. Even though within that group, every person had just as much chance of being selected as any other Hispanic. That's a probability sample. So it's based off percentages when you start. That's maybe another way to think of this, based off percentages. So let's take a look at a little bit of a example here. You're trying to find out what students in your school think about stem cell research. Okay? You select students in your statistics class of all places. I would argue that, well, because you're already talking about statistics, that's probably a convenient sample. It was just easy to do. You didn't put any effort into it. You didn't put any thought into it. And definitely, because you're talking about the school, not every student had an equal chance of being selected. So it's definitely not random. That is a convenience sample. You assign each student a number and question every 25th student, starting with the 8th student. And that number 8 was chosen by a random number generator on your calculator, which I'll be showing you later on how to do. So the machine picked where to start. You just picked the increments afterwards. Of course, that's going to be random systematic. It is random. Everybody had just as much. It's not simple random because it's not groups. It's random because it's individuals, and it is a systematic study. You randomly, by some process, I haven't described one here, choose people from each grade to question. Now, each grade, so second grade, third grade, fourth grade, that's a stratified random. It is random and it's stratified. You choose and survey 10 random. So again, you've done something here to randomize it. First hour classes. Now, you didn't pick which people were in those classes. You just picked the classes. So you went to 10 different classrooms during first hour. Which classrooms you go to, those were picked randomly. Who's in those? Well, that was already done. So that's a cluster. They've been naturally clustered, in this case, by the administration on who's going to be in which class. So hopefully this helps give you an idea of the different kinds. All right, designing an experiment. More terms, more vocabulary. Confounding variables. I already kind of mentioned this with that depression one. If it's sunny outside, then you may not be getting an accurate thing because you got a variable, the weather, that really throws a monkey wrench into the deal. So, confounding variables when you're not able to distinguish between the effects of different factors. Was it the exercise that made them less depressed? Or was it the fact that the sun was out? It's hard to tell, so it's a confounding variable. The placebo effect. Untreated subjects report improvement. So, some people are given medication, some people are given a sugar pill, but there's certain ones that just because they were given a pill, they somehow feel better. That's referred to as the placebo effect. Blinding. The subject does not know if they are receiving treatment or placebo. They're getting a pill, they don't know which one it is. Double blinding. The person giving the pill doesn't know which pill is which. In most medical research, it's double blinded. The nurse administering the medication, doesn't know if she's giving the placebo or if she's giving the treatment. Because what they found in the past, remember, statistics were developed through error. They found when it was just blinding that the nurse or the doctor or whatever, just with their body language, was giving away which thing they were getting, the treatment or the placebo. So they had to go to double blinding. So even the person giving it doesn't know which one they're giving. So then it's a third party. Completely randomized design. Randomness is used to assign subjects to treatment groups. So now you don't even know who's going to end up with which one. Back in the day, they just said, okay, you, and you're going to, the doctors would decide, or the researchers, those people there, they're going to get the treatment. Those people over there, they're going to get the placebo. Complete random design says, no, we're taking the researcher out of it, and they're going to randomly assign who's going to be in the treatment, who's going to be in the placebo. Random again, everyone has just as much chance of being in one as in the other. Not that they're 50-50. It's just that it's not up to the person which group they're going to be in. Match pairs design. In two treatment groups, so both groups getting treatments, such as a treatment and a placebo, the matched pairs are somehow related or have similar characteristics. Maybe they're the same age or the same gender or the same ethnic group. Or here's the one that a lot of researchers just love, twins. Okay, so you can have twins, one receiving the treatment, one receiving the placebo. Or maybe you're pairing twins against twins. I don't know. But the twins are an easy one to understand. One's getting treatment, one's getting placebo. Which one gets it might be random, maybe not. But match pairs just means that somehow you've got two things that are matched up, and one's getting treatment, one's getting placebo. All right, I know it was a long one today. I got a lot of stuff for you to take a look at. Back on page 3, I want you to read, why was the Literary Digest so wrong? On page 19, example 2, there I want you to look at the answer of what went wrong with the Literary Digest poll. I want you to read Misleading Statistics in Journalism. Now, it's a column article. It's just a little article on the side of page 18. Then I've got some practice for you to do. Now, guys, these are kind of a 1-2, skip a few. Look at a category, do a couple things, do a little bit of practice. You don't necessarily have to do everything because a lot of the questions are more of the same. kind of once you feel like, yeah, I got this, well, then move on to something else, okay? But make sure you practice it until you feel comfortable that you've really got that. And then I also, one more thing is, again, this is a little column article. It will not take long on page 27. Clinical trials versus observational studies. Please read that. Don't worry about the calculator stuff I've got here yet. I will be getting you into using calculators later on. All right, have a good day.